After all this, you may be wondering by now, is there a need for network admins and networking knowledge in the cloud? And the answer is absolutely. There are multiple network services that will need to be configured and managed once running in the cloud. So, if you're a network admin and already have this knowledge, you may be a true asset as part of your organization's cloud migration strategy. Before jumping into Cloud ACI and its benefits, let's take a deeper look into how cloud networking works without using ACI, using AWS networking services as example. Let's log into the AWS console. As you can see, we're currently working in the US East region. The very first thing we need to do is create a VPC, which is similar to a VRF. As you can see, each account has a default VPC, and you may be wondering if it wouldn't be easier for us to use that one. The reason to avoid the default VPC is that it comes with a default configuration that would not meet security best practices, and that's why creating your own VPC is always recommended by AWS in this case. In the cloud, IP addresses are automatically associated to instances or VMs. In order for this to happen, we must create a CIDR block as part of the VPC configuration. The CIDR block is your main IP address block so that you can later create subnets from it, which will be assigned to the different availability zones in your region. With this in mind, CIDR blocks are usually large networks with /16 to /28 subnet masks as minimum. Internet connectivity for the VPC is provided by an Internet Gateway or IGW, which you must create and attach to your VPC as well. After this, you need to create your subnets from the main CIDR block. Each subnet you create will be mapped to an availability zone and can be private, meaning that they won't have direct connectivity to the internet, or public, which as we will see next, may have internet-facing connectivity using a public or elastic IP address. Anything we configure in terms of networking through a VPC will only apply to this region. Therefore, if you need geographical redundancy, you may have to configure a VPC and its corresponding configuration for each additional region. Every subnet you create is going to be private by default, so if you want to enable them to become public, you just have to adjust its settings so that VMs in such subnets get both a private and a public IP address. For private IP addresses, cloud providers commonly reserve the first 3 usable IP addresses per subnet and automatically assign the rest. This is important to know, especially if you're migrating from an on-premises environment and want to keep the same IP address in the cloud, as we will cover in Module 5. If you want instances on private subnets to have indirect connectivity to the internet, you can enable functions on the cloud, like NAT gateways. Just like on-prem VRFs, every VPC has its own routing table. There's a main default routing table that includes your main CIDR block. If I added the gateway to the main routing table with a quad 0 route, I would expose all related subnets from the main CIDR to the internet, which is not necessarily what you want. Therefore, you have to create your own routing table, and then you would need to associate the specific subnets to this routing table, and finally, you would also need to adjust the routes so that they reflect the IGW as your default gateway. Now, if you go to EC2 to create an instance, you have to choose the cloud network settings, assigning the right subnet and availability zone to the cloud VM NIC. In the case of AWS, such NICs are known as Elastic Network Interfaces or ENIs. There are other types of NICs that you can also use, such as ENAs and EFAs, which may provide accelerated connectivity and low latency features for specific needs. As with on-prem, you can provide multiple ENIs or network adapters to your instances. When ENIs are associated to public subnets, they will have a private IP automatically assigned as covered before. And they will also have a public IP which can be your own or which can be automatically assigned by the cloud provider, in this case AWS. As covered before, remember that whether you use public or private subnets, AWS recommends that instead of using the main routing table, you create your own routing tables to have better traffic control. In the cloud, it's not only about routing, CIDR, and subnets only. Security is embedded by default following a policy model, which is very similar to Cisco ACI. This means that you must explicitly grant access to your cloud resources, otherwise communication will not be allowed. In the case of AWS, there are two main ways to achieve segmentation and define policy between different segmentation groups. The most popular one is called security groups, which is similar to ACI EPGs. They are used to control inbound and outbound traffic and are assigned per instance. Instances in a security group need rules to communicate to other security groups, prefixes, and more. Every new security group you create will allow all outbound traffic by default, while denying all inbound traffic until you explicitly adjust it, following an allow list model. As mentioned before, security groups and their rules are comparable to ACI EPGs and contracts or firewall security zones. Just like with ACI, endpoints in the same security groups have unrestricted communication by default. All security group rules are stateful, meaning that you do not need to create any mirror rules. In the case of AWS, there's another option that can be used to control traffic at the subnet level, which is called NACLs or Network Access Control Lists. All subnets are associated to a default NACL, which rules are set to permit all traffic both inbound and outbound. Therefore, unlike SGs, you do not need to customize or adjust NACLs if you do not want to. NACLs are not stateful, and they can have both allow and denied listing. If we take a look at this diagram taking AWS as reference, instances in the web security group will have free communication between them, while communication from the web security group to the database security group, or even the internet, will require specific rules to be manually defined by the administrator. It is important to mention that cloud networking services are entirely based on Layer 3, meaning that there is no Layer 2 forwarding configurations, such as VLANs, broadcast traffic is not supported, and multicast is either not supported or limited depending on the cloud provider you use. The concepts we learned about before will very likely have different names and implementation options in all the different clouds. For example, in Azure, instead of VPCs and security groups, we may be talking about VNets, ASGs, and NSGs. And in case of Google Cloud, we will simply talk about VPCs and firewall rules. As networks scale, understanding, configuring, and managing all these concepts may become challenging. We just covered an overview on how communication works for a single region and VPC in AWS. But what if we needed multiple VPCs, regions, and clouds to communicate? Or even if we needed to provide connectivity from our on-prem environment to different clouds? Going back to AWS as our reference for this chapter, there are multiple options we can use. The first one is VPC peering, which may be useful for single and multi-region inter-VPC connectivity. However, it does not support transit communication and requires point-to-point configuration, making it hard to scale and manage. As a second option, we have hub and spoke configurations, where there is normally a hub or transit VPC and multiple spoke VPCs. For these type of setups, AWS Virtual Private Gateways or VGWs are commonly used at the spoke level, while routers like CSR1000B are used at the hub level. IPsec connectivity is established between each hub CSRs and spoke VGWs on each VPC. While VGWs can also be used to connect site-to-site VPNs as well, CSR routers are commonly deployed as EC2 instances to connect to on-prem environments and other clouds, since it allows organizations to maintain a common operation model plus a richer feature set. It is important to mention that this implementation option has a 1.25 gigabits maximum bandwidth limit for each tunnel, and that CSRs are charged by AWS just as with any EC2 instance. BGP is commonly used to exchange routing information between clouds and sites. We will be covering hybrid and multi-cloud connectivity in Module 5, where we will learn about multi-site ACI, so stay tuned. As a third option, we have transit gateways or TGWs, which can also help communicate different VPCs in a single region or even in multiple regions through transit gateway peering. TGW is an interconnect hub service that the different VPCs attach to, allowing higher bandwidth per attachment than VGW and also offering VPN connection options to external environments. However, CSR1000B can also be used in conjunction with TGW for external connectivity to on-prem sites and across clouds for the same reasons mentioned before. TGWs are the preferred option to use for inter-VPC communication, especially since it uses the cloud provider backbone network. You just have to attach each VPC to the TGW service using a subnet or subnets on different availability zones from each VPC CIDR, and the TGW will automatically pull the CIDR information as part of its routing table. Keep in mind that on each VPC that you attach to the TGW, you will need to add static routes to other VPC CIDR blocks pointing out to the TGW as the next hop in your routing table. In this case, the orange VPC would have a route to the blue VPC CIDR pointing out to the TGW as next hop, and the same thing would happen in the other case around. In AWS, when connecting on-prem environments to your instances on the cloud, you may simply use the internet and connect through your VPC IGW. You may also run site-to-site IPsec VPNs over the internet, which can be terminated using any of the options mentioned before, or you can also use a high-bandwidth private physical connection from the cloud provider, which in the case of AWS is called Direct Connect. Direct Connect may run directly to the cloud provider facilities or through a colocation partner. These same concepts apply to all cloud providers with their specific names and differences. If you now add your on-premises environment to the mix, network administrators in a hybrid cloud environment may find operational challenges to provision, monitor, and secure the network consistently. This is where Cloud ACI may help, since you only need to learn one networking model, not many, allowing you to normalize network operations across multiple clouds. Cloud ACI abstracts the network configuration and automatically creates the corresponding network configuration on each cloud. Cloud ACI can run in a single cloud or may also automatically interconnect multiple clouds using VXlan, BGP, and optionally IPsec through multi-site orchestrator. This approach accelerates cloud adoption and keeps both configuration and security consistent across multiple types of clouds while reducing the learning curve. We will learn how to run and configure Cloud ACI as well as the difference it makes when comparing to what we did today in the next chapters. As a summary, networking knowledge is very much needed in the public cloud as well. Although there is different terminology for each cloud provider, the concepts are very similar to what you already know. There are multiple networking elements you will have to configure and manage as we learned today, which may increase complexity and potentially add inconsistency to your multi-cloud environment. As we will see next, ACI can help automating the creation of your network configuration across multiple types of clouds, unifying and normalizing your operational model without sacrificing any cloud-native services. Not only is this important to provide connectivity and identify issues faster, but also to keep security consistent by defining your configuration once and letting ACI enforce it anywhere.